Hello everybody, welcome to lecture 19. So our theme today is still the characteristic polynomial of a square matrix. We're in section 3.5 and today will be our last main lecture really in chapter 3, although we might have a few loose ends to tie up next week. But really what we need to talk about today is the process by which we can calculate the characteristic polynomial of any square matrix of any size, not necessarily just 2 by 2. And in order to see that, we need to talk a little bit about determinants. So let's just recall the key concepts first of all. So if we take a 2 by 2 matrix, A, B, C, D, we know that the characteristic polynomial of that matrix is the determinant of the expression for the matrix lambda times 2 by 2 identity minus A. That matrix has lambda minus A, lambda minus D on the main diagonal, minus B in the upper right, and minus C in the lower left. So its determinant is lambda minus A times lambda minus D, the product of the two entries on the main diagonal, minus the product of the other two entries. So when you expand that, it turns out to be lambda squared. We've got lambda minus lambda times A plus D. And then as a constant term, we've got a plus AD here and minus BC. So the coefficients of the characteristic polynomial basically are one for the leading term, the quadratic term. We've got minus A plus D times lambda, and we've got the constant term AD minus BC. And we can observe that the coefficient of lambda here, A plus D, is the trace of A, nothing but the sum of the entries on the main diagonal of A, and that the product, or sorry, the constant term in the polynomial, AD minus BC, is nothing but the determinant of the matrix A itself. So the trace and determinant of A turn up in the coefficients of the characteristic polynomial. The leading coefficient is always 1. The characteristic polynomial is what they call a monic polynomial. That means that it's the coefficient of its highest order term is always 1. Now, if we think about this polynomial as being a polynomial whose roots are the eigenvalues of A, as we know it is, then if lambda 1 and lambda 2 are the two eigenvalues, then the polynomial can be written as lambda minus lambda 1 times lambda minus lambda 2, lambda 1 and lambda 2 being the two roots. And if we expand this product, the version of it that's written in terms of the roots, and compare the coefficients to the version written in terms of the entries of the matrix, then what we can observe is that the coefficient of lambda in this latter product is minus lambda 1 plus lambda 2, which is minus A plus D, so that lambda 1 plus lambda 2, the sum of the two eigenvalues, is nothing but the trace of the matrix A. And we can also observe that the product of the two constant terms here, lambda 1, lambda 2, should be equal to the constant term up here, which in terms of the entries is AD minus BC. So the eigenvalues of a 2 by 2 matrix have the property that their sum is the trace of the matrix, and that their product is the determinant of the matrix, which is a kind of nice and useful fact. So, you know, in general, of course, unless the matrix is diagonal or triangular, we don't expect that the eigenvalues would just be the entries on the main diagonal. But we're saying here that the sum of the two eigenvalues is equal to the sum of the two entries on the main diagonal. That's certainly an easy thing to calculate. Not only that, but the product of the two eigenvalues is the determinant AD minus BC. So that's certainly a useful way to think about eigenvalues. And also sometimes if you want to calculate them, it can be a shortcut or an alternative way of doing so, at least for 2 by 2 matrices. So some version of this statement is true in general. It's a little bit more complicated because there are more coefficients around than just a constant term, a leading term, and a constant term, a leading term, and a linear term. But nevertheless, the trace, determinant, and other particular combinations of entries of the matrix do turn up in the coefficients of the characteristic polynomial, and they have expressions in terms of the roots also. Okay, so the eigenspace, of course, of A corresponding to either of the eigenvalues, lambda 1 or lambda 2, is the null space of the matrix that we get by replacing the variable lambda here with that particular eigenvalue that we're interested in. So lambda 1 identity minus A or lambda 2 identity minus A. And the non-zero elements of that space are the eigenvectors of A corresponding to lambda 1. Okay, so in order to extend this discussion to n by n matrices in general from 2 by 2s, we're going to have a chat about the determinant of a matrix, which is defined in general for any square matrix. Its definition in the 2 by 2 case is pretty straightforward because it's a fairly manageable combination of the entries in that case, but its definition in general gets more complicated rapidly as n increases, or at least gets more convoluted, if not necessarily more conceptually complicated. So where does the determinant come from anyway? And why do we talk about it? Why do we care about it? What's its, why is it defined? So I guess it turns up in the question of whether a matrix has an inverse or not. And to answer that for any 2 by 2 matrix at all, we have the following equation satisfied. if we have a 2 by 2 matrix whose entries are A, B, C, D, and we from it define this related matrix obtained from A by switching the two entries on the main diagonal, the A and the D, and by changing the signs on the other two entries, so changing B to minus B and C to minus C. This is a matrix assembled from A according to an explicit instruction. And then if we multiply the original A by this thing, we can observe that what happens is we get a diagonal matrix with the same entry in every diagonal position. So we get AD minus BC in the top left from row 1 of A and column 1 of this newly defined matrix. We get minus AB plus BA, which is 0 in the upper right. We get CD minus DC, which is 0 in the lower left, and we get minus BC plus AD in the lower right. So we get the diagonal matrix whose entries in all the diagonal positions are the same. They're all equal to AD minus BC, that expression in the entries. And so our matrix then is just the 2 by 2 identity matrix multiplied by this scalar, AD minus BC. Okay, that's true for any 2 by 2 matrix, and it's just, we can check it directly. So conclusions, well, first of all, if the number AD minus BC is equal to 0, then this equation tells us that A is not invertible. Okay, if A is already the 0 matrix, then certainly it's not invertible. But if it's not the 0 matrix, then at least one of these columns, D minus C or minus BA, is not the 0 column, but both of those columns are in the null space of A. If the determinant AD minus BC is 0, then over here on the right-hand side, we have the 0 matrix. So we're saying that we have non-zero columns that can be multiplied by A to give us the 0 vector. That tells us that A is not invertible. Okay, that's just equivalently saying that the columns of A don't form a basis for R2 or F2 for whatever field we're working with. Okay, if the determinant, if the expression AD minus BC is not 0, though, in our field, then this equation can be rearranged by just dividing it through by the reciprocal of that scalar AD minus BC to say that the inverse of A is this matrix, D minus B minus CA, multiplied by 1 over AD minus BC. And we can just check directly that if we multiply A by this thing, provided that the denominator here is not 0, we get a perfectly good statement that A multiplied by this matrix in either of the two possible orders is equal to the 2 by 2 identity matrix. So nobody would be surprised by any of this. It's all familiar to all of us. What it's telling us is that the matrix A has an inverse if and only if the number AD minus BC is not 0. Not only that, it's telling us how to write down the inverse as well. But that means that the number AD minus BC, which is a pretty easily computed expression in terms of the entries of A, really tells us something about A. It tells us whether or not the columns of A form a basis. It tells us whether or not the columns of A are linearly independent, which is a valuable thing because we're interested in bases and in linear transformations. We care about linear independence and we care about invertibility. So we have this number that can be calculated from the entries of A that tells us whether A is invertible or not, or equivalently tells us whether the columns of A form a basis for two-dimensional space or not. Okay, so this does carry over to 3 by 3, 4 by 4, and so on, which is remarkable that given any square matrix, there's a number that we can calculate in terms of its entries that tells us by virtue of whether the number is 0 or not, whether the columns of the matrix are linearly independent or not. The downside is that the process of computing it becomes quite a bit more intricate and more labor-intensive as the size of the matrices increases. So we're going to look at the 3 by 3 case, but also within that, we're going to define the concept of the determinant for general matrices. Just a bit of terminology and lingo that goes with all of this. So the equation here that's satisfied for every 2 by 2 matrix prompts some definitions. So first of all, we talked about this already, but the number or field element, whatever it is, AD minus BC, the product of the two diagonal entries minus the product of the other two, that's called the determinant of the matrix A, and it's often denoted by DET brackets A. Sometimes it's denoted by A with vertical bars around it. Personally, I prefer the notation DET A because I think this kind of absolute value style notation is quite overutilized in mathematics and potentially can lead to confusion. But certainly if you're reading about this anywhere, you'll often find the determinant of a square matrix denoted by the name of the matrix with vertical bars around it. That's quite standard. Okay, another piece of notation or terminology. This matrix, which multiplies by A to give the determinant times the 2 by 2 identity, that is called the adjugate of A, and it's often denoted by ADJ for adjugate. Sometimes it's called the adjoint. You might come across that, but adjugate is a more correct name for it because adjoint means various other things as well. I've never seen the word adjugate used except in this particular context. Okay, that's the story for 2 by 2s. So I suppose what we're going to do is write down a similar description for 3x3s that will actually extend to square matrices of all sizes. The 2x2 version is a representative example of this, but somehow the 3x3 version contains enough complexity to sort of show how the story will go in general, and the 2x2 case doesn't really quite do that. Okay, so the version of the adjugate equation for a 3x3 matrix is written here. So it's a complicated thing to read. We'll have a look at it for a minute. So the setup here is we're giving ourselves a general 3x3 matrix with entries A, B, C, D, E, F, G, H, I in the 9 positions. We don't know much about this matrix. It lives over some field, let's say the real numbers. Its entries can be anything, and we don't know, for example, whether its columns are linearly independent or anything like that. Okay, so the assertion is, and I'm asking you to kind of believe this, and you can check it directly, that the version of the adjugate equation for a 3x3 is what's written here. So it's a lot to read, but what we're saying is we start with this matrix A. Here's another 3x3 matrix assembled from the entries of A in some way. We'll come back to that in a second. And the claim is that if we multiply these two matrices together, and this is something that you can easily check, then what you get is the diagonal matrix that has zeros in the 6 off-diagonal positions, the upper right and lower left areas. And in the main position, in the 3 positions on the main diagonal, it has this number repeated. Okay, so that number is an algebraic expression in the entries of A. In the 2x2 case, it was just AD minus BC. Here it's something more than that, but it doesn't look so dissimilar in some ways, because if we look at the 6 entries that turn up here in this expression, here it is written again. Each of them is the product of 3 entries of A, AEI, AFH, BDI, BFG, and so on. And each of them is the product of 3 entries of A with the property that the 3 of them all appear in different rows and in different columns. Okay. And basically there are 6 products of that type. If you want to write down a product of 3 entries of A, where each of the 3 entries comes from a different row and different column of A, then basically you have a choice of 3 entries to choose from the first row. Multiply that by one of the 2 entries in the second row that isn't in the same column where you chose the first entry. That's 3 times 2. And at that stage, you have only one choice left for an entry to choose in the third row, which isn't in either of the first 2 columns, represented by the first 2 entries. So 3 factorial, or 6, is the number of such products that you have. All 6 of them appear here, some of them with negative signs. And this at least resembles, in a sense, the 2x2 version, where our matrix is AB in the first row, CD in the second. And what we have for the determinant is a sum of the 2 products of a pair of entries of A that come from a different row and different column. That's the 2 entries on the main diagonal, and the 2 entries, the 2 off-diagonal entries. So in that case, there are only 2 such products. One of them appears with a negative sign, the other with a positive sign. In the 3x3 case, there are 6 such products, and okay, we'll talk again about which ones appear there with positive and negative signs. Okay, so this expression is called the determinant of A. So I'm not asking you to kind of memorize what it is as an expression involving the entries of A at all. We will be able to calculate with it, but that's what it is. Okay, so obviously it's already kind of substantially more complicated than the determinant of a 2x2. To calculate it according to this formula, you have to calculate 6 different products of 3 entries of A. Okay, what about this 3x3 matrix? So again, as in the previous 2x2 case, we had a 2x2 matrix here whose entries were D, A on the main diagonal, minus B, minus C. The other 2 positions, they were all entries of A, some of them adjusted with a sign. What we have here are not entries of A, but various sort of quadratic combinations of entries of A. Each of these expressions is the sum of a product of 2 entries of A, one with a negative sign. This matrix is the adjugate of A, again, for a 3x3. And if we look at what the actual entries are of this thing, we might observe that each of the 9 entries of the adjugate of A here looks like a 2x2 determinant. It's the product of 2 things minus the product of another 2 things. And if we look at what the entries actually are in each of these expressions, the first one in the top left, EI minus FH, that's the determinant of the 2x2 submatrix that's in the lower right corner of A. Top in the center position of the first row here in the adjugate of A, we have the product CH minus BI. That is minus the determinant of the submatrix of A consisting of the entries BC from row 1 and HI from row 3. and so on. Each of the 9 expressions here you can check is either plus or minus the determinant of a 2 by 2 matrix that remains when a row and column are deleted from the matrix A. So this is consistent with the 2 by 2 case, although it's not obviously true. In the 2 by 2 case, when you delete a row and column, you're left with a 1 by 1 matrix. So its determinant is just its single unique entry. Here, if we delete a row or column, we're left with a 2 by 2 matrix. And the determinants of those 9 2 by 2 matrices are what is going into this adjugate matrix in some order. Okay, so to figure out exactly what the order is and what everything looks like, let's introduce, as usual, a little bit more notation. So here is the same equation written in a slightly different way. So again, this is the matrix A. This 3 by 3 matrix is the adjugate of A. It's the same matrix that we had before. It's just written differently to emphasize the fact that its entries are 2 by 2 determinants. This is the 3 by 3 identity multiplied by the determinant of the matrix A. So, okay, we're saying that if we take A, B, C, D, E, F, G, H, I, multiplied by the 3 by 3 matrix, and look at what the entries are in the various positions here. The entry in the 1, 1 position is the determinant of what remains when the first column and first row, so the row and column of the 1, 1 entry, are deleted from the matrix A. We're left with E, F, H, I. Determinant of that is EI minus FH, which is the top left entry of the adjugate of A. Okay, if we go to the top center entry, so here it is. It is the determinant, well, it's minus the determinant of what remains when the entry in the 2, 1 position, second row, first column, when its row 2 and column 1 are deleted from the 3 by 3 matrix A that we started with. What's left is BC in row 1, HI in row 3, and the determinant of that 2 by 2 matrix appears with a negative sign in the 1, 2 position of the adjugate. Okay, so the entry in the 1, 2 position of the adjugate is minus the determinant of the matrix that remains when the entry of the 2, 1 position, when its row and column are deleted from A. If we go to let's go to the 3, 2 position, which is this F in A. Okay, the entry in the 2, 3 position of the adjugate. So we're talking about the 2, 3 position of A, where this F is. The entry in the 2, 3 position of the adjugate is the determinant of the matrix with AC in the first row, GF in the second row with a negative sign. That is the 2 by 2 matrix that remains when the 3, 2 entry, which is where this H is, when its column and row are deleted from A. That leaves AD in column 1 and CF in column 3. Okay, so this adjugate of A, somehow it's a matrix assembled from the determinants of the 2 by 2 matrices that remain when the 9, when in turn, for each of the 9 entries of A, its row and column are deleted from A, and we look at what's left. Okay, here's a couple of definitions. So the minor, denoted Mij, of the entry in the ij position of a 3 by 3 matrix is the determinant of the 2 by 2 matrix that remains when row I and column j are deleted from A. So the minor, for instance, of the 3, 1 entry is the determinant of what remains when row 3 and column 1 are deleted from A. That's BCEF. Its determinant turns up here in the 1, 3 position of the adjugate. Okay, here's another definition. Closely related, the cofactor, Cij, of the entry in the ij position of A is either equal to the minor or to the negative of the minor, depending on what position we're in. And which one it is determined by this pattern of signs. So basically, if you're in a position that's labeled here with a plus sign, like the 1, 1 position or the 1, 3 position or the 2, 2 position, in those situations, the cofactor of the entry in that position is defined to be equal to the minor. If you're in a position that's labeled by a negative sign, like the 1, 2 position or the 2, 1 position or the 2, 3 or the 3, 2 positions, in those cases, the minor is the negative, the cofactor is the negative of the minor. Those are the 4 positions that are labeled with negative signs up here in the determinant description of the adjugate. Okay, so just be careful with this description. So I'm absolutely not saying that the cofactors are positive in the positions marked plus and negative in the positions marked minus. That's not it. What it is that in the positions marked plus, the cofactor is the same as the minor, and in the positions marked minus, the cofactor is the negative of the minor. So it could be positive or negative depending on whether the minor is positive or negative. Okay, so the adjugate of the 3 by 3 matrix A, which is given up here in general description, it's the matrix whose entry in the ij position is the cofactor of the entry of the ji position of A. Okay, so the adjugate of the matrix A, if we were to write out the matrix of cofactors with the entry in the ij position equal to the cofactor of the entry in the ij position of A itself, then we would get the transpose of the adjugate. So the adjugate is the transpose of the matrix of cofactors of A. Okay, so it's complicated, but basically the transpose, the adjugate is the key to whether A is invertible or not, just as for the 2 by 2 case. If the determinant is 0, then this equation basically says A is not invertible. If the determinant is not 0, then this equation tells you how to write down the inverse of A. It's just the adjugate multiplied by the expression 1 over the determinant, which is a sensible thing to write down if the determinant is not 0. Okay, so that's how the adjugate and determinant of a 3 by 3 matrix are defined. And I guess really the key point is this description of the adjugate. This enables us to write down a 3 by 3 determinant and to calculate it. Once we know how to do a 3 by 3 determinant, then basically using the same kind of thinking, we can develop a 4 by 4 determinant and we can build up the n by n determinant. A remark about the cofactor equation for a 3 by 3 matrix. So, I'm not claiming for a second that it comes from anywhere obvious or that we should be able to see immediately why it's satisfied. But I guess if we go back to the first slide on this topic, you can verify directly by just doing the multiplication that this matrix product is indeed equal to the 3 by 3 identity matrix multiplied by this expression, which we're calling the determinant of the 3 by 3 matrix A. Okay, so to calculate 3 by 3 determinants then, here's what we can do. If we look at any of the 3 entries of the main diagonal of the product A multiplied by the adjugate of A, what are we saying? So here, if we look at this description of A multiplied by the adjugate of A, the determinant of A appears in each of the 3 diagonal positions of this product. And what that's saying is, for example, looking at the top left position, if we take the entries A, B, C of the first row of A, multiply each of those entries by the entry in the corresponding position of the first column of the adjugate of A, then we get the determinant. Okay, so you can check that, of course, directly, maybe using the version on the previous slide, which is a bit easier to use for that purpose. Okay, so what are we saying then? Well, okay, the entries in the first column of the adjugate of A are the cofactors of the entry in the first row of the entries in the first row of A itself. Okay, so the determinant, the entry in the upper left position of this product, is the sum over all the entries in the first row of A of each one of them multiplied by its own cofactor. The cofactors are either equal to the minors or the negatives of the minors. In the first row, the only position where it's the negative of the minor is the middle, the second position. Okay. Equally well, if you want to look at the 2-2 entry of this product instead of the 1-1 entry, that comes from the second row of A, scalar product with the second column of the matrix of the adjugate of A, which again involves each of the entries of the second row of A multiplied by its own cofactor, and those 3 quantities added together. So by looking at the 3 entries on the main diagonal of the product A by adjugate of A, or adjugate of A by A, which it has the same value, it's determinant times the identity, we have this description of the determinant of a 3 by 3 matrix. So the determinant of a 3 by 3 matrix A can be found by choosing any row or column of A, calculating the cofactors of the entries in that row or column. That means calculating the minors and adjusting them by signs where necessary, and adding the results. Okay, so it's still a fairly labor-intensive process compared to the 2 by 2 determinant, but it involves calculating 3 2 by 2 determinants and then taking each of their products with an entry of the matrix A and adding those together. Okay, so that's a definition that can, now that we know how to calculate 3 by 3 determinants, we can repeat this process basically to define determinants of matrices of greater size, but it's kind of a recursive definition. Okay, so I guess this is the sort of takeaway point at this stage, that the determinant of a 3 by 3 matrix can be obtained by taking any row or column of the matrix, calculating the cofactors of the entries in that row or column, multiplying each of the 3 entries by its own cofactor, and adding those together. If you happen to have the good luck to choose a row or column that has some zeros in it, you don't need to bother calculating the cofactors of those 0 entries, because when they get multiplied by 0, they don't contribute anyway. Okay, that's the definition basically of a 3 by 3 determinant, and it comes from the adjugate equation. A few general remarks about determinants. First, each of these definitions applies to n by n matrices in general. And what we're really saying is that they give us a way to define an n by n determinant in terms of smaller determinants. Okay, so we've basically defined a 3 by 3 determinant in terms of 2 by 2 determinants by saying, if we want to calculate a 3 by 3 determinant, we pick a row or column of our matrix, we calculate the cofactors of the entries in that row or column. Those are 3 2 by 2 determinants. We multiply each of the 3 entries by its own cofactor, add those together, and that is the determinant of the 3 by 3 matrix. Okay, once we've done that, we can now do it for 4 by 4s as well. And the adjugate equation for a 4 by 4 works extremely similarly to the adjugate equation for a 3 by 3, except that it's even more horribly complicated to write down. So again, the adjugate of a 4 by 4 matrix is the transpose of the matrix of cofactors of the matrix itself. But its entries now, each of them is the determinant of a 3 by 3 matrix that remains when one row and one column are deleted from the 4 by 4 matrix. So the adjugate of a 4 by 4 matrix has 16 entries, 4 times 4. Each of them is a 3 by 3 determinant, okay, just as the adjugate of a 3 by 3 matrix has 9 entries, each of which is a 2 by 2 determinant. But once we know how to calculate 3 by 3 determinants, we can calculate the cofactors of a 4 by 4 matrix. The pattern of signs in the 4 by 4 case has the same general appearance. It starts with a plus in the top left and then just alternates minus plus throughout the first row and throughout all the subsequent rows and columns. Okay, so generally we can define determinants of n by n matrices in terms of determinants of smaller matrices. Okay, this method for computing determinants is referred to as the cofactor expansion method. It is not generally the most efficient way to compute a determinant. So really, its value to us now is more as a definition of a determinant than as a means of computing a determinant. So it's not so bad in the 3 by 3 case, which is the worst that we will actually do. It's not even so bad in the 4 by 4 case, but it rapidly gets worse. You know, so for example, to compute a 10 by 10 determinant using the cofactor expansion method, you have to compute 10 9 by 9 determinants. Each of those involves 9 8 by 8 determinants. Each of those involves 8 7 by 7 determinants, and so on. So you know, the level of complexity and effort and labor involved in computing an n by n determinant grows kind of factorially in n. It gets unwieldy very, very quickly. So in practice, if you actually want to know what the determinant of some matrix is, which is a reasonable thing to want to know, if you want to know, for instance, whether the matrix is invertible or whether its columns are linearly independent, in practice, a more efficient method is to use elementary row operations to reduce the matrix to triangular form, and then to make use of some properties that we know about how elementary row operations affect the determinant. So this is related to comment number 3 here, which is that in some cases, the determinant is easier to compute. So if A has some special form, for example, if A is upper or lower triangular, so upper triangular means that the entries along the main diagonal of A and above the main diagonal may be non-zero, but that all entries in the lower triangular region below the main diagonal are non-zero. So if a matrix is upper triangular, then its determinant is just the product of the entries on its main diagonal, and you can actually confirm that using the cofactor expansion method with the first row, for example, to start with. Or the first column maybe is better for an upper triangular matrix. Okay, a lower triangular matrix is the transpose of an upper triangular matrix. So it's got 0 entries in the upper triangular area above the main diagonal and potentially non-zero entries on and below the main diagonal. So its determinant also is a product of entries on its main diagonal. If a matrix is diagonal, which means it has no non-zero entries at all, except possibly on its main diagonal, then that's an example of a matrix which is both upper and lower triangular. And again, its determinant is just the product of its entries on the main diagonal. So the matrix is invertible in that case if it has no zeros on its main diagonal. Okay, and the other remark that I just make is that if you have a matrix which has a square k by k block in the upper left area, and then a square block of the complementary size n minus k by n minus k in the lower right area, and has just zeros in the rectangular block, kind of that's down in the lower left corner. So it's, then its determinant is just the product of the determinants of these two square blocks. Okay, that's not really obvious, but it's not too difficult to deduce using the cofactor expansion formula. Okay, then the fourth property, which is something that's really important and definitely needed all the time, and a really, really useful property of determinants, but not at all obvious, is the so-called Cauchy-Binet formula, or the multiplicative property of determinants. And what it says is that if you have a pair of n by n matrices A and B, then the determinant of their product is the product of their determinants. This is not hard to check for 2 by 2 matrices. Even for 3 by 3s, it's a bit of a chore, but it can be done. It's not really easy to check at all once it gets any bigger than 4 by 4, but it is a true statement. And when you look at the definition of the determinant in terms of cofactors, in terms of taking a row or column of the original matrix, calculating all the cofactors of the entries in that row or column, multiplying each by its cofactor and adding them all up, it is not remotely obvious why it should be true that process should somehow respect the multiplication operation for matrices, that the determinant of the product AB should be equal to the product of the two determinants. We're not going to prove that. It is true, and it's something that's going to be very valuable to us for lots of reasons. Okay, so what we're going to do next, and we'll just make a start on it now and we'll return to it next time, is just use what we now know about 3 by 3 determinants to calculate the characteristic polynomial of a 3 by 3 matrix. So the theory that defines the characteristic polynomial is exactly the same. Okay. If B is this 3 by 3 matrix, the characteristic polynomial of B is the determinant of lambda times the 3 by 3 identity matrix minus B. Okay, because basically we're looking for values of lambda for which this matrix is not invertible, so that there will be non-trivial solutions to the equation B times some vector equals lambda times some vector. That requires that lambda times the identity minus B not be invertible, so that its determinant be 0. So now that we know how to calculate a 3 by 3 determinant, our main purpose for doing that right now, and for using the cofactor expansion method for doing this rather than searching for some simpler or more efficient method, is that we want to calculate characteristic polynomials. And I guess here, for a characteristic polynomial is the determinant of some matrix where there's an unknown variable on the main diagonal. So really the cofactor expansion method is the main method available for computing a determinant like this. If we have a fixed matrix whose entries are all specified numbers, then there's a possibility of reducing it to, for example, lower triangular form using elementary row operations and deducing its determinant from that. But for a characteristic polynomial, we can't really do the elementary row operations so easily because we have this variable hanging around. Okay, so that's the introduction to the determinant, which we haven't talked about a lot in this course, and we're not going to talk about it very much more, although there is literally no end to what can be said about determinants. But we leave it at that point for now and resume in week 11 with the next lecture. So thank you everybody for joining this one, and see you next time.